So the next speaker is Professor Daniel Xiapu from the Hong Kong Polytechnic University. So Professor Daniel is a professor in the Department of Computing and the Director of the Research Center for Blockchain Technology at the Hong Kong Poly U. So his research focuses on the blockchain and smart contract security. So he is one of the top researchers in the smart contract and mobile and IoT security, network privacy, and software engineering. He has published extensively in the top-tier venues and received many Best Distinguished Paper Award, such as the ACM 6 Soft Award and Best Paper Award from Infocom and others. So Professor Daniel regularly serves as the program committee's member of the Reading Security and Software Engineering conferences, and also be recognized with the top Reviewer Award from top conferences. He is Associate Editor of IEEE ACM Transaction on Networking, the Transaction on Dependable and Secure Computing, and ACM Transaction on Privacy and Security. So let's welcome Professor Daniel and listen to the talk. Thank you.
Thank you so much for the kind introduction. I would also like to thank the organizers for the invitation. So today is my great pleasure to be here to introduce our recent study on discovering vulnerabilities in blockchain ecosystems and to learn from all of you. So since Bitcoin started and Ethereum introduced smart contract, the blockchain world has really taken off. As shown as the figures. Unfortunately, the underlying blockchain platforms and smart contracts may not be as secure as what you expect, with many blockchain platforms and smart contracts vulnerable to attacks. At the same time, there are also many, so for example, this web page shows that the cyber attacks on blockchain have led to more than 33 billion in financial loss. At the same time, there are also some of the white hats helping developers identify and fix vulnerabilities. Then you may wonder why there are so many vulnerabilities and attacks. One possible reason may be due to this principle or catchphrase in the blockchain community, that is code is raw. Meaning that the code of the blockchain and the smart contract will be the true ultimate authority. But can we really follow this principle or rule? Currently, the answer may be no. Because you may expect that, as a developer or user, you may expect that the smart contracts or blockchain platforms are bug-free and they have been thoroughly audited. Unfortunately, there are many known or unknown vulnerabilities in smart contracts and blockchain platforms. So yesterday, there are already several interesting talks pointing out the vulnerabilities in blockchain platforms, network, as well as the smart contracts. And you may also expect that the blockchain infrastructure are secure and robust. Unfortunately, they are also vulnerable to attacks. For example, yesterday there are talk on the robustness of blockchain network. Professor Tang also mentioned the vulnerability in the memory pool of Ethereum. And you may also think that you are calling the right smart contract that will do what you expect or what they claim. Unfortunately, there are also many fraudulent or scam smart contracts that have been deployed in the blockchain. And you may also think that the smart contracts, once deployed, cannot be changed. Unfortunately, they can be changed, although the data written into blockchain cannot be changed. So there are also many other reasons. So these slides are showing the major components in the blockchain ecosystem, including the user front end, interacting with layer 1 or layer 2 or layer N infrastructures via the internet. There are also some third-party service, such as the smart contract verification service. And on top of these platforms, we have applications, different types of applications written in smart contract that will be called by the users. And you may wonder which part will be vulnerable to attacks. Our research, as well as the research, the related work introduced by other experts, have shown that all of them could be the target of attacks. So my research aims to develop a holistic way to safeguard the blockchain ecosystem from two aspects. One is to identify vulnerabilities. In particular, we focus on uncovering zero-day vulnerabilities. So those are the vulnerabilities have not been known by the developers and someone else. And we also develop a new approach to accelerate the vulnerability discovery for smart contracts and blockchain platforms. And we also propose approach and tools to help developers detect and fix bugs. Another direction is to defend against various attacks targeting on blockchain platforms as well as smart contracts. So in this talk, I will focus on the part of vulnerability discovery. Actually, we have uncovered many severe vulnerabilities in layer 1 blockchain blockchains, as well as layer 2 blockchain platforms, such as Arbitrum, Optimism, and Polygon. And we also unveiled the vulnerabilities in the third-party service, such as the Ethereum smart contract verification service. And we also have some ongoing work targeting on other layer 1 or layer 2 platforms. Besides, we have been working on discovering the vulnerabilities in smart contracts running on different types of runtimes, such as the Ethereum virtual machine, WebAssembly runtime, Algorand virtual machine. So some of us are in the Algorand center. The Move as well, even the Bitcoin script. Okay. So in today's talk, I will focus on the vulnerabilities we have discovered in blockchain infrastructures, if time permit, but I don't think so. I will also introduce how to speed up the vulnerability discovery for smart contracts. So yesterday, Professor Tang talked about the DOS attack on the Ethereum's memory pool. Today, I will introduce another type of DOS attack relevant to the gas mechanism. So the DOS attack can break down the whole Ethereum, the whole blockchain platform, because all the nodes follow the same set of protocols. The gas mechanism was proposed by the Ethereum to prevent resource abusing by charging for each execute instruction on the EVM. So this table lists the cost of different types of instructions. Unfortunately, it's not that easy to properly set the gas cost. That means nowadays, the gas cost may not truly reflect the resource consumption. So this issue has been exploited to launch DOS attacks on the Ethereum and its variants. Basically, those attacks involve continuously calling some underpriced instructions to deplete the computational resource of blockchain nodes, such as this one occurred in 2016. But please know that such attacks will only have a temporal effect. That means once the attack stops, the blockchain platform will return to normal. Then let's consider another question. Can we discover some attacks that will have persistent effect? on the blockchain platform? The answer is yes. So we recently discovered a new attack targeting on the state storage of Ethereum and its variants using the MPT structure. And after even the attack stops, the effect of the attack will continuously impact the performance of Ethereum and its variants. Let me first introduce some background knowledge related to this attack. So the blockchain state storage is usually managed by the data structure. MPT, or the Merkle-Patricio tree, was chosen by Ethereum and many other blockchain platforms. Of course, they are considering replacing it with other new data structures currently. And in the MPT, a leaf node stores the value of the persistent data. And the path from the root to the node corresponds to the key of this value. Our attack were motivated by two observations. One is the fall in the gas mechanism. So that is the gas cost is not equal to the real resource consumption. Let me use an example to explain it. So here we have three EOA accounts, including the AAB3E, ACD3F, and ABC60. Okay, so they are organized in this, they are stored in this MPT. So, and we also have two transactions. One transaction is like this. The AAB3E will transfer a certain amount of Ether to ACD3F. And in the second transaction, this account, AAB3E, will transfer the same amount of Ether to this account, ABC60. So according to the Ethereum specification, these two transactions will cost the same amount of gas. So that is the 21,000 units of gas. However, the resource consumed by these two transactions are not the same. The reason is that the first transaction will involve the multiplication of 6 nodes in the MPT. But the second transaction involves the multiplication of 9 nodes in the MPT. So the 6 nodes is the AAB3E as well as the ACD3F. But in the second transaction, the 9 nodes will be a fact. Okay. The second observation is that most operations with MPT are the major performance bottleneck of the existing blockchain. So recent studies show that 80% of the execution time of blockchain was spent in the interaction with the MPT structure. Moreover, we find that the time cost of major time-consuming operations in interacting with MPT linearly increase with the number of nodes in MPT. Okay? With these two observations, we proposed the new attack named Nergo. The basic idea is to strategically manipulate MPT to impair blockchain's performance. More precisely, we try to increase the number of intermediate nodes in MPT so that we can raise the time cost in interacting with state storage. Once those new nodes are introduced to MPT, they will not be removed so that even the attack stops, the effect will still be there. And we proposed several strategies for introducing new nodes into MPT. The first one is to, say, split this leaf node into another leaf node as well as a branch node. And the second strategy is to split a leaf node into an extension node, a branch node, as well as a new leaf node. And the third strategy is to split a leaf node into a branch node and a new extension node. So the details could be found in our paper. Here I will just briefly mention the strategy. And we also perform some experiments to evaluate the effect of Nergo on Ethereum as well as other blockchain platforms using MPT. Due to the ethical issue, we only launched the attack on the Ethereum and BSC testnet. So actually, we conduct experiment on 6 major blockchains testnets. And the experiment showed that the Nergo can effectively increase the intermediate node in their MPT, and then increase the number of MPT nodes to be modified to update a leaf node. And moreover, Nergo can cause more than 30% more MPT nodes to be invoked, and also raise the cost time of state modification by more than 15%. So this is the first work. So the takeaway message of this work is that the gas cost is not equal to the real resource consumption. And in this work, we identify a new attack vector that can cause a persistent effect on blockchain using MPT. And we have reported this vulnerability to all those major blockchain platforms. They have acknowledged us with bug bounties. And now they are considering how to replace MPT with another type of data structure to address this issue. In terms of the attacks with temporary effect, we have also done some interesting work. A recent work is this one, published in ISTA. We developed a tool to identify manipulable performance bottleneck in blockchain clients. By triggering those performance bottlenecks, we can also launch the DOS attack on the blockchain platforms. Then let's move up to the layer 2 platforms. We identify some double spending vulnerabilities in popular layer 2 platforms, such as Arbitrum, OP, Polygon. So layer 2 solutions are built on top of a blockchain, for example, Ethereum, to improve the scalability and efficiency by handling the transactions off the chain. Rollup is a major type of layer 2 solutions that will ensemble multiple transactions and send them in a single batch to the main chain. The layer 2 as well as the rollup, especially the rollup solutions, have already gained popularity. Existing rollup solutions can be roughly divided into 2 categories. One is the optimistic rollup, and another one is the ZK rollup. So in this talk, we will focus on the optimistic rollup. So simply put, the optimistic rollup will process the transactions on layer 2 and send the transaction data to layer 1. Although different optimistic rollup implement the protocol differently, they share some common components. For example, they will have a L2 node serving as the execution engine for the L2 blockchain. They will have a sequencer that will put the received transactions into an ordered sequence. And there will also be a batch submitter that will periodically assembles the sequenced transactions into batch and then submit them to L1. You can also find a validator that will send the state rule of the L2 blockchain to the L1 smart contracts. This figure shows the transaction life cycle of Arbitrum. And we got this figure after carefully reading the documents and screwing their source codes. The transaction life cycle consists of 2 stages, including the soft finality and hard finality. A transaction reaches the soft finality state once it is received and processed by the sequencer. And the transaction reaches the hard finality state after the batch, including this transaction, has been included and finalized on Ethereum. In this figure, we use blue lines to trace the transaction's journey from acceptance to the soft finality. And we use the pink lines to illustrate the progression from soft finality to hard finality. It's worth noting that once the L2 transactions reach the hard finality state on L1, the L2 node will fetch the hard finalized transaction from L1 and compare them with the soft finalized transaction on L2. If there is any discrepancy between them, the L2 node will roll back those soft finalized transactions. So these are the most important things we leverage to launch the double spending attack. We propose this double up roll attack to launch the double spending attack in Arbitrum as well as the OP. So we have another interesting observation motivating us to propose this attack. That is, the third-party applications, such as the cross-chain bridges, will act on the transactions once the soft finality has been achieved rather than the hard finality. Then, what if an attacker can force Arbitrum to roll back the state change caused by the transaction as soft finality? The answer is the attacker can launch the double spending attack. For example, the attacker can send a transaction to Arbitrum asking the cross-chain bridge to mint tokens on another chain. And since the bridge will do that once the transaction reaches the soft finality state, the attacker can collect the tokens, immediately collect the tokens, and then try to roll back the transaction on L2. Then the attacker can get the tokens without paying any money. We identify 3 mechanisms in Arbitrum that can be exploited to launch the double spending attack, including the time-bound mechanism that is used to limit the degree to which the sequencer can adjust the block timestamp. And the second one is the liveness preservation mechanism that is used to provide censorship resistance even when the sequencer becomes unresponsible or malicious. Simply put, the user can call the Arbitrum's forced inclusion to submit a cross-chain transactions. And the third one is the transaction compression and decompression mechanism. I will focus on the third one for the ease of explanation, because to understand these 2 mechanisms, I need another hour. So during the transaction synchronization between L1 and L2, the batch submitted from L2 will be compressed. And following the inclusion in L1, the compressed batch will be fetched by the L2 node. The L2 node will decompress them and into the sequence transactions. And then you will compare it with the transactions in the soft finality at layer 2. If there is any discrepancy between these 2 types of transactions, the transactions in the soft finality state will be rolled back. Then how to roll back the state? A simple approach is to create an invalid batch. Then how to create an invalid batch? And of course, we also need to consider the time, because the attacker needs to send a cross-chain deposit transaction, and the attacker also needs to collect the token and then roll back the transaction. Okay. Then we have another 2 observations. One is that if the target transaction is delayed in reaching the hard finality, it remains in the soft finality state and becomes vulnerable to rollback. And to exploiting the time-bound and liveness preservation mechanism, we also need to delay the target transaction for a certain period. And we propose a new attack to manipulate the delay duration of the target transactions in order to successfully trigger the state rollback. This figure shows the basic idea of our manipulable delay attack. The basic idea is very simple. That is, we will construct large size incompressible data. So those are random generated data so that they cannot be compressed by existing compression algorithms. And then we will append the data to many L2 transactions and send the transaction to the L2. Then let's see what will happen. The batch submitter will try to compress this transaction into batch. But since these transactions contain impressible data, their size will not be changed so much before and after the compression. And in this case, each transaction will be packed into a separate batch. And then the batch submitter will publish this batch to the L1 one by one, okay? Since the block interval of layer 1 or Ethereum is about 12 seconds, and the batch submitter will wait for the L1 confirmation, it will take a long time to publish this batch to L1. And so we can manipulate the delay. Okay. And then we propose 3 double spending attacks, including the overtime attack, exploiting the time-bound mechanism, the kill card attack, exploiting the liveness preservation mechanism, as well as the Z-bomb attack. That exploit the 4 in the transaction compression and decompression mechanism, calling the state rollback. Simply put, the flaw occurs because there is a size-bound check during decompression, but not during compression. In this case, we can exploit this flaw to create some invalid batch. So here I will briefly introduce this Z-bomb attack. So it's a little bit complicated. So the attacker will first introduce a delay by sending the incompressible transaction, and then the attacker will send a series of transactions. Those are the bump, okay? That will have a very high compression rate. And then the attacker sends a cross-chain deposit transaction. The batch submitter will first compress the transaction and pack them into a batch before submitting them to L1. Since the bump transactions have very high compression rate, they can be put into so one batch will contain many such type of bumps, okay? And during the induced delay, the attacker can do what they want. For example, to send the cross-chain deposit. And due to the large delay, the batch will not be immediately submitted to L1, but the cross-chain bridge will process this deposit transaction and means the tokens on the target chain. And then the attacker can collect these tokens. And once the L2 node retrieves the batch bomb from L1 and decompress it, since the size of the decompressed data will exceed the limit, the L2 node deems it to have invalid transactions. So that this cross-chain deposit transaction in the soft finality state will be rolled back. And then, but the attacker have already collected the tokens, mean on the other chain. Okay, so we found that some of our proposed attacks can also be launched on Optimism. And all of the vulnerabilities have been confirmed and acknowledged by the developers with many bug bounties. Our research have prevented billions of dollars in loss. Then I guess you may wonder whether ZK rollups will have similar issues. The answer is yes. We also have found similar issues in Polygon ZK rollup. The result will appear in our another CCS paper this year. I guess I do not have time. I will quickly go through the vulnerability we found in the smart contract verification service. Now there are One reason is that it's not easy or very challenging for us to understand the meaning or the functionality of smart contracts, because it's not that easy to understand these bytecodes. Then how to do that? That comes the source code verification service. That is that given a piece of deployed smart contracts, anyone can submit a request with a piece of source code as well as the compilation options to the smart contract verification service, saying that I have the source code of this deployed smart contract bytecode. And the smart contract verification service will combine the source code with the provide options, and then they will compare the generated bytecode as well as the deployed bytecode and see whether they're the same. If they're the same, the smart contract verification service will mark the source code as the one that can generate this piece of bytecode. So these are, we investigate all major source code verification service. So this figure shows their general architectures. Due to the time, I will not go through the details. But here I would just like to mention two types of attacks that can be launched by exploiting the vulnerabilities in the smart contract verification service. And our paper appears in this year NDSS. The first one is called adversarial verification. That is, given a benign smart contract bytecode, the attacker can submit a piece of source code containing maybe malicious issue, meaning, or vulnerable functions. And by exploiting the vulnerability of the source code verification service, this piece of source code will be regarded as the source code of the benign smart contract bytecode. And another type of attack is called a source scam. That is, the attacker may want to deploy a malicious smart contract bytecode, but he or she will first submit the source code without any malicious actions. After this source code has been, after the corresponding bytecode has been marked as legitimate, the attacker will replace the one with a malicious one, with a malicious attacks. Malicious smart contract, sorry. So we have investigated these three major source code verifiers. We identify 8 types of vulnerabilities. Most of them have been confirmed and patched, but for either scan, we contact them, but they didn't reply to us. Due to the time limit, I will just use 2 examples to explain this attack. The first one is due to the unchecked simulating. And the sourceify has a simulating component that will tell you whatever you receive as the creation code. Now, basically, the smart contract bytecode combined from the source code contains of 2 types of codes. One is the creation code that will be run to initiate and generate the runtime code. The runtime code contains the real business. And the sourceify uses its own simulating component to run the creation code and then generate the runtime code. But we identify a vulnerability that can be exploited to bypass its simulating component. That is, in normal case, the runtime code pointer is obtained using the code copy opcode, and which is found at the end of the creation code. The runtime code is then returned and executed. But due to the vulnerability, the attacker can construct a piece of code which will explicitly return a pointer that points to the victim's runtime code before the actual code copy. So just like this. We can put the legitimate smart contract bytecode here, and then we return it explicitly, rather than waiting for the code copy opcode. And the sourceify will regard this one as the runtime code generated by the created code. Okay, the second one is how to deploy malicious smart contract to replace the legitimate one. So actually, we can create, so I believe most of you may know this opcode, create2. We can use create2 to update the on-chain contracts. Okay, So due to the time, I would like to use this figure to conclude my talk. So there have many hidden vulnerabilities in existing blockchain ecosystems. And therefore, currently we cannot strictly follow the Coase law principle. Instead, more research needs to be done, and more experienced auditor need to be trained to work together to uncover those vulnerabilities. Okay, that's all my talk. Thank you so much.
Thank you very much. Okay, again, due to the time limit, so maybe we can have a question during the lunch, or maybe one question here, please.
Yeah, thank you very much for this interesting talk. So I have a general question. You talked about attacks. Can you also comment on mitigation part?
Yeah, that's a very good question. So we talk about 3 types of attacks targeting on different components in the blockchain ecosystem. So for the first attack, targeting on the data storage. So one possible solution is to replace the MPT with another type of data structure. So Ethereum and other blockchain platforms are working on them. But our recent study showed that those new data structures may also contain vulnerabilities. For the second one, the vulnerabilities in the layer 2 infrastructures, they have already patched those vulnerabilities. They use many mechanisms to address those issues. For example, the compression and decompression mechanism, they add the new checking. For the type-bound mechanism, they use other approach to streamline the batch generation and so on. And for the third-party service, actually, we found that many vulnerabilities are similar to those traditional vulnerabilities in the web service. So after we report those vulnerabilities to them, they have fixed the vulnerabilities. Okay, thank you.
Okay, thank you very much. And we would like to thank everybody for attending this session, and we have the lunch later. So please wait for the announcement.
Now I would like to invite Prof. Wen to facilitate the speakers.